Dear students, let us continue our study in this paper Organic Chemistry, and in this particular module we shall study about two named reactions, Claisen condensation and Mannich reaction. And as a matter of fact, both of these reactions you will feel that they are quite related with the aldol condensation that you have already studied. After studying this module, you shall be able to know about the basics of both these named reactions, that is Claisen condensation and Mannich reaction. You shall be able to identify the major product formed in crossed Claisen condensation and Dickman condensation, which is nothing but intramolecular Claisen condensation. You shall be able to evaluate and apply the mechanistic details of the Claisen, Dickman condensation and Mannich reaction, and you shall become familiar and you shall be able to know the applications of these named reactions. Dear students, in the previous modules we have studied how the aldol condensation provides an excellent way for making new carbon-carbon bond, and it joins two molecules or moieties which are aldehyde and or ketones, and at least one of them has alpha hydrogen in them. And this is done by using base like sodium hydroxide. Here, if you recall, the base OH minus abstracted the alpha hydrogen and gave rise to alpha carbon ion, which is stabilized via the enolate ion, and this further attacks as a nucleophile to another aldehyde or ketone. The question now comes to our mind is that in a similar manner, if we wish to join two ester molecules, how could this be done? If we take ester and add NaOH as base to generate alpha carbon ion, you already know it will undergo hydrolysis and rather not generate the alpha carbon ion. So, the answer to this is that if sodium alkoxide is used, it will not affect the ester functional group and yet generate the required alpha carbon ion. And this is what is precisely done in the Claisen condensation, which we will be studying in this module, whereby the esters are condensed to give rise to beta keto esters as the condensation product. We can very well say that Claisen condensation is nothing but aldol applied to esters. We shall study the Claisen condensation in detail in this module. Another interesting thing is that when Claisen condensation is done with diesters, that is the same molecule having two ester functionalities, then it will lead to intramolecular Claisen ester condensation and it will give rise to cyclic beta keto esters, and then this is called as Dickman condensation. So, we will be studying the Claisen and then extending to Dickman. But another challenge comes when we have to join formaldehyde with any other aldehyde or ketone through mixed aldol condensation. At the initial site, formaldehyde seems to be the ideal electrophilic partner in a mixed aldol reaction, as it cannot enolize because it is not having any alpha hydrogen. And furthermore, aldehydes are more electrophilic than ketones, you already know. But the problem is that it is too reactive and it will tend to react more than once and it will give rise to extra unwanted reactions, even from Cannizzaro reactions that you are already familiar. So, one way of carrying out the addition of formaldehyde to an aldehyde or ketone is through Mannich reaction. So, this is the second major reaction that we will be studying in this module, and this Mannich reactions involves an enolizable aldehyde or ketone plus a secondary amine and plus formaldehyde, which is taken in its aqueous solution, and all this combination is done in the presence of HCl as catalyst. The product so formed is a beta amino ketone, and this is known as Mannich base. The amino group we will study can be removed and it helps you condense the formaldehyde with any other aldehyde. Ultimately the thinking where we started, and this Mannich gave us help that how we can combine formaldehyde with any other aldehyde or ketone. So, we shall study about the Claisen condensation, its intramolecular part which is Dickman condensation, and the Mannich reaction. So, let us first begin with the Claisen condensation. Here you can see is the general reaction, and this reaction is named after Rainer Ludwig Claisen. And if we talk about the Claisen condensation, it is a carbon-carbon bond forming reaction that occurs between two esters, as you can see here, in the presence of sodium alkoxide as base, resulting in beta keto esters. Obviously, you can notice here the alcohol is the byproduct. Now, this reaction can be considered as aldol reaction applied to esters. But rather than using hydroxide ion as base to generate the alpha carbon ion, alkoxide ion is used as the base. You are already aware that esters would hydrolyze if hydroxide ion is used, and hence the appropriate base to generate the alpha carbon ion is alkoxide ion. For example, when ethyl acetate reacts with sodium ethoxide, as you can see in this equation, then ethyl acetoacetate is obtained as the product. So, using this example, let us try to understand the mechanism of this reaction, and parallelly we will compare it with aldol reaction of acetaldehyde. So, the first step in both of them you can see is the formation of enolate ion via the abstraction of proton forming the alpha carbon ion. And from acetaldehyde, as you can see here, the abstraction is done by OH minus as the base, and the difference in case of ethyl acetate, the ethoxide ion abstracts the alpha hydrogen to generate the corresponding enolate ion. The next step in both the cases is again similar. It is the nucleophilic attack by the enolate ion on the unenolized carbonyl compound or the ester. In aldol reaction of acetaldehyde, as you can see here, the enolate ion attacks as a nucleophile to another molecule of the carbonyl compound at the carbonyl carbon. And in the Claisen reaction, there is a similar attack of the enolate ion generated from ethyl acetate to the carbonyl carbon of the ester group of the unionized ethyl acetate. After this nucleophilic attack, the Claisen condensation and aldol addition, they differ in their mechanism. In the aldol addition or the aldol condensation, the negatively charged oxygen so obtained will be taking a proton from the solvent and leads to the product, which is the beta hydroxyaldehyde or ketone that you are already aware. On the other hand, in the Claisen condensation, the negatively charged oxygen reforms the carbon oxygen double bond and expels the alkoxy group, which you know it is a good leaving group, so it goes out. And thus the Claisen condensation is a nucleophilic substitution reaction, while the aldol condensation is a nucleophilic addition reaction. So, this you can see as shown in the equations here. So, the first one you can see here, the completion of the aldol, how it happens and gives rise to this beta hydroxyaldehyde, and in the Claisen you get this particular beta keto ester. Even though the last step is different, the two products are quite similar. You can notice both of them are dimers of the original 2 carbon chain in a sort of way, and they both have carbonyl groups at the end of the chain and oxygen substituents at the beta or the third position in reference. The two reactions obviously belong to the same family, as it is evident by their similar mechanism, and that is why I said the Claisen condensation you can consider it is the aldol applied on the esters. And note that in the Claisen reaction, the alkoxide ion is used as the base, this OR minus of the alkoxide ion must be the same as that of the alcohol part of the ester on which you are reacting, because else it will lead to the mixture of products through the trans esterification reactions as well. So, after understanding this mechanism with correlation with the aldol, let us take another example and understand its mechanism. Let us consider the Claisen ester condensation of this methyl propionate, as you can see here. So, starting from this methyl propionate, this particular one is the alpha hydrogen which is being attacked by alkoxide, which is the methoxide ion here. Notice that in the ester now it is COOCH3. So, the methanol is the alcohol part of the ester. So, we will be using methoxide ion and not ethoxide, propoxide or any other alkoxide. So, this methoxide ion will be taking out this particular alpha hydrogen, and as a result you can see the methanol is the byproduct, and then the alpha carbon ion is getting generated, which is stabilized by the enolate ion, you know. And through this alpha carbon ion, this entire species will be attacking as a nucleophile to another ester molecule at the carbonyl carbon, resulting in this species which is alkoxide ion, and this is the new CC bond form which is there between these two molecules. And further on, this alkoxide ion will be expelling out the OCH3 minus, which is a good leaving group, and the resulting is this beta keto ester. Notice that the methyl here is coming in the side because the alpha carbon has attack on the carbonyl carbon of the another ester molecules. So, this is how the mechanism goes. Note that expulsion of the alkoxide ion is reversible because the alkoxide ion can readily reform the tetrahedral intermediate by reacting with the beta keto ester. The condensation reaction can be driven to completion, however, if a proton is removed from the beta keto ester. Removing a proton prevents the reverse reaction from occurring, because the negatively charged alkoxide ion will not react with the negatively charged beta keto ester anion. It is easy to remove a proton from the beta keto ester because its central alpha carbon is flanked by two carbonyl groups, making its alpha hydrogen much more acidic than the alpha hydrogens of the ester starting material. So, this you can see, it is shown here that the equilibrium between the beta keto ester and how the CH3O minus can attack to give you this alkoxide ion, and after the removal of another alpha hydrogen, it will give you this beta keto ester anion. So, consequently, a successful Claisen condensation requires an ester with two alpha hydrogen and an equivalent amount of base rather than a catalytic amount of base. When the reaction has been completed, addition of acid to the reaction mixture reprotonates the beta keto ester anion, and any remaining alkoxide ion that could cause the reaction to reverse would also get protonated, as you can see, which is shown in these equations. So, you can see here this beta keto ester anion can get protonated again, and here also you can see there is another example which is shown for the Claisen condensation, where you are having the ethyl propanoate, but notice that this time to carry out the Claisen condensation, the base used is ethoxide ion, because it is same as the ethanol part of the ester, that is OCH2CH3, that taken as the base, and later on after acidification you get this particular beta keto ester. And you can notice that these are the two parts of the two molecules which have joined, and the ethanol is the byproduct here. After the Claisen condensation, just like the aldol, here also we can have crossed Claisen condensation. Claisen condensation between different ester reactants will be called as crossed Claisen reaction. The cross Claisen reactions in which both the reactants can serve as donors and acceptors will obviously give you complex mixtures. Because of this, most crossed Claisen reactions are usually not performed unless one reactant has no alpha hydrogens. So, for example, you can consider this is a very good example of cross Claisen condensation. There are these two esters and you can notice that this methyl benzoate has no alpha hydrogen. So, this will act as a recipient, and in case of this methyl acetate, it will act as donor by generating the alpha carbon ion. And obviously, the base used here is NaOCH3, that is a methoxide ion, and this will give you this particular beta keto ester on this reaction. After the Claisen condensation, let us now move to Dickmann reaction, which is nothing but the Claisen carried out in an intramolecular manner. The addition of alkoxide base to a 1,6-diester causes the diester to undergo a intramolecular Claisen condensation, thereby forming a 5-member ring ester. And whenever intramolecular Claisen condensation takes place, we classify them or give them the name of Dickmann condensation. For example, you can consider as shown here in this equation, this is cyclization of dimethyl ester of adipic acid, that is, it is dimethyl hexane dioate. If you look at the mechanism of Dickmann condensation is just the same as the mechanism of Claisen condensation. The only difference between the two reactions is that there the attacking enolate and the carbonyl group undergoing nucleophilic attack are different molecules in case of Claisen condensation, but both of these moieties, that is the attacking nucleophile and the carbonyl where the attack will happen of the ester, are in the same molecule in case of Dickmann condensation. The Dickmann condensation, like the Claisen condensation, is driven to completion by carrying out the reaction with enough or sufficient base to remove a proton from the ester product. When the reaction is over, the acid is added to reprotonate the condensation product, and you can look at the mechanism here that this particular diester, when reacted with CH3O minus, any of these alpha hydrogens can be taken out, and this alpha carbon ion when formed, rather than this attacking on another molecule, it will prefer the intramolecular attack, because this carbonyl of this ester is electron deficient, and this leads to the cyclization as you can see here. So, this alkoxide ion formed, and this alkoxide ion will drive away the OCH3 minus, which is a good leaving group, and leads to this beta keto ester, which is a cyclic ketone. So, this is the 5-member cyclic beta keto ester which is formed in this particular case. Let us consider another example. It is not that always you will get 5-member, it depends upon where the two esters are positioned. So, you can get any member ring for that matter. So, in this another example, you can clearly see a 6-member beta keto ester is getting formed from the Dickmann condensation of a 1,7 diester. So, notice that here again the alpha carbon ion formed at this particular carbon will be attacking on this carbon, and this is how you are getting this 6-membered cyclic beta keto ester. After the Claisen and Dickmann condensation, let us now move to the Mannich reaction or Mannich condensation. Named after the chemist Karl Mannich, it is an organic reaction which consists of an amino alkylation of an acidic proton placed next to a carbonyl functional group by formaldehyde and a primary or secondary amine or ammonia. The final product is a beta amino carbonyl compound which is also referred to as Mannich base. So, this general reaction you can see as shown here. So, this is the amine, and you can see it is reacting with formaldehyde and with another aldehyde or ketone, and this is how the condensation happening, and we will see the mechanism in detail. It is an example of a nucleophilic addition of an amine to a carbonyl group followed by dehydration. The Schiff's base is an electrophile which reacts in the second step in an electrophilic addition with a compound containing an acidic proton. The Mannich reaction is a condensation reaction. So, in this reaction, it is primary or secondary amine or ammonia which are used for activation of formaldehyde. We can say the tertiary amines, they lack NH proton to form the intermediate enamine, and that is how they will not be participating in this. Alpha CH acidic compounds include the carbonyl compounds, nitrile, acetylenes, aliphatic nitro compounds, alpha alkyl pyridines or imines. It is also possible to use activated phenyl groups and electron rich heterocyclics like furan, pyrrole and thiophene. Indole is particularly active substrate. The reaction provides gramine derivatives. So, these are the various extensions which the Mannich reaction can go into. So, let us consider this very simple example and understand the mechanism. Let us look at this reaction of cyclohexanol with dimethylamine and formaldehyde which is taken in its aqueous solution, and this combination is done in the presence of catalytic HCl, and this product you can see is the amino ketone which is formed. In the mechanism involves the preliminary formation of an imine salt by the combination of amine and formaldehyde. The amine is nucleophilic and attacks the more electrophilic of the two carbonyl compounds available, that is out of any other aldehyde or ketone, and formaldehyde, it will be the formaldehyde which will be obviously more electrophilic. So, no acid is needed for this addition step, but acid catalyzed dehydration of the addition product will further give rise to imine salt as you can see here. So, in the normal Mannich reaction, this is just an intermediate, but it is quite stable, and the corresponding iodide is also sold as Asymmetric salt for use in Mannich reactions. So, you can directly start with that and do the reaction with any other carbonyl compound. Further, how the reaction takes place, let us understand. The electrophilic salt can now add to the enol. Why enol? Because the medium is acidic medium and the other carbonyl compound, here in case of this example we have taken this cyclohexanone, will be converted into its enol form in the acidic medium as you can see here. So, this enol form will be then attacking on this electrophilic salt, and followed by deprotonation you will get this combination which is the Mannich product as the Mannich base, which is this ketoamine. And notice that the position of amine is at beta in reference to keto, just like the aldol condensations and Claisen condensations we have seen. So, by using this reaction we can add one molecule of formaldehyde to a carbonyl compound, and note that this product is not actually an aldol product. However, it remains a very important reaction because it is a simple way to make amino ketones, and many drug molecules they belong to this class. Furthermore, the Mannich products can be easily converted into enones, and the most reliable method for making the enone is to alkylate the Mannich base with methyl iodide and then treat with ammonium salt with base. The enolate ion formation leads to even Cb reaction rather than like the dehydration of aldols, but with a better leaving group. So, you can see this elimination happening. We are starting with this amino ketone which is the Mannich base or the Mannich product, and then reacting with methyl iodide through SN2 you get this salt which is this, and then further it will undergo removal via even Cb to give you this enone, and this double bond is at relatively alpha beta position. Enones like this with two hydrogen atoms at the end of the double bond are called as exomethylene compounds. Notice that this double bond is outside the cyclic ring. So that is why the name exo. So these are the exomethylene compounds, and they are very reactive and cannot be otherwise easily made or stored. So they certainly cannot be made by aldol reactions with formaldehyde alone, as we have seen. So the solution to prepare such good molecules which can be further utilized is through the Mannich base, store them and then to alkylate and eliminate only when the enone is required, and this is in the Michael reaction. So these enones will be further utilized. If the enone is to be obtained as the product, the secondary amine does not end up in the molecule, so the more convenient or the less volatile and less smelly cyclic amines, pyrrolidine and piperidine, are often used. Enones with mono-substituted double bonds can be made in this way, as you can see in these examples. After understanding the Mannich reaction, let us understand asymmetric Mannich reactions. When properly functionalized, the newly formed ethylene bridge in Mannich adduct has two prochiral centers, giving rise to two diastereomeric pairs of enantiomers. The first asymmetric Mannich reaction with an unmodified aldehyde was carried out with S-proline as a naturally occurring chiral agent, as you can see here. So you can notice that here this combination is happening and you are getting these diastereomeric pairs of enantiomers. So I am sure now you are very clear about these named reactions, that is Claisen condensations, its application on intramolecular reaction, which is Dickman condensation, and then Mannich condensation. So let us now summarize what we have learnt in this module. Because esters contain alpha hydrogen, if we have to generate their alpha carbon ion, then rather than aldol, which utilize OH minus as the base, we have to use OR minus, the alkoxide ion, as the base, and that is what is precisely done in Claisen condensation. So Claisen condensation is nothing but it is the aldol condensation when applied to ester by using appropriate base, which is alkoxide ion, and the product formed is a beta keto ester, and the mechanism we studied in detail. The intramolecular reaction of Claisen condensation is called as Dickman condensation, and it can lead to 3-member cyclic ring, 4-member, 5-member, 6-member, depending upon what diester you start with. Then we also studied about the Mannich reaction, and the Mannich reaction is amino alkylation reaction involving the condensation of an enolizable carbonyl compound which has alpha hydrogen, which is acidic, with a non-enolizable aldehyde, it is formaldehyde most of the cases, and with ammonia or a primary amine or a secondary amine, and these three will combine in the presence of acidic medium, and the resulting is the Mannich base. Since the beta aminocarbonyl compounds can be conveniently reduced to beta amino alcohols which show considerable pharmacological activity, the Mannich reaction plays very important role in pharmaceutical chemistry.